today's topic is curvilinear coordinate. In curvilinear coordinate, there are two type of coordinate. One is spherical polar coordinate and another is cylindrical coordinate. Let's first discuss the spherical polar coordinate. In spherical polar coordinate, we have three axes which are x-axis, y-axis and z-axis. Now x, y, z are used for Cartesian coordinate. We have to convert these coordinates into r, theta, phi, which are used for a spherical coordinate. Now let's take a point P. Now the point P is at a distance r from the origin, and this straight line making an angle theta with z axis, and the perpendicular from this point on xy plane is called PQ. Now this we connect this Q point and this origin, and this line makes an angle with the x-axis which is called phi. So in case of curvilinear coordinate, we are discussing spherical polar coordinate. So in case of spherical polar coordinate, we take to define a point P, we first look for the distance for origin and that point, which is denoted by r, the angle that r makes with the z axis, which is denoted by theta, and we take perpendicular from the point P on xy plane and then join the origin and that point, and the point that straight line makes an angle with x-axis which is called phi. So we define spherical polar coordinate with respect to point r, theta, phi. Now as this straight line is r and this angle is theta, so obviously this component on z axis will be r cos theta, and the component on this OQ, this let's call the point origin O. So the component on this point OQ is called r sin theta. Again, if we think about the direction of the of the unit vector at this point P, we can see that the direction of r will be along r axis, that is r cap. Now the direction of theta will be along this perpendicular to r cap, which is theta cap, and the phi, the direction of phi will be in the remaining direction, that is phi cap. Now the component on as this OQ line is r sine theta and this angle is phi, so we can say that the component on x axis, which is denoted by x, is r sine theta cos phi. So x equal to r sine theta cos phi. For the direction y, we can write y equal to r sine theta sin phi. As this straight line is r sine theta and the component on y axis is called r sine theta sin phi, and the component on z axis is directly already given, that z equal to r cos theta. Now if we square these three terms, that is x square plus y square plus z square, we can see, if we write like this, that x square plus y square plus z square, we can see that r square sine square theta cos square phi plus r square sine square theta sine square phi plus r square sine what is the value of z again? Z is r cos theta, so r square cos square theta. Now if we take common r square sine square theta, we can see that we will get cos square phi plus sine square phi, which has a value of 1. As we know, cos square phi plus sine square phi equal to 1, and plus we have r square theta. Then we get r square sine square theta plus cos square theta. We are taking the r square common and we get r square. So we can write r equal to root under x square plus y square plus z square. So this is how we find out the magnitude of this vector, and to find theta, we can see that this angle is called theta. So we can already write z equal to r cos theta. So we can say z by r equal to cos theta. We could write that z equal to r cos theta. So we can write z by r equal to cos theta. So from here we get the value of theta equal to cos inverse of z by r. And to find the value of phi, we can see that we can divide the x by y. So if we divide x by y, the r sin theta terms get vanish, and we can only get cos phi and sin phi. So if we divide x by y equal to, we get cos phi by sin phi. Then if we write it in the reverse order, we get y by x equal to sin phi by cos phi, which can be written as tan phi. So we can write it as phi equal to tan inverse of y by x. So this is how we find out the value of phi, the value of theta, and the value of r. So this is the three parameter on which we define the spherical polar coordinates. Now in spherical polar coordinates, a vector can be expressed in this way, that AR, that means the vector component along r cap direction, AR r cap plus A theta theta cap plus A phi phi cap, where AR, A theta, A phi are the vector component along r, theta and phi direction, and r cap, theta cap and phi cap are the unit vector along those direction. Now if we take a infinitesimal displacement in r cap direction, we can write that value will be dr. However, if we take infinitesimal element of length in theta cap direction, we can write that value as r d theta. And if we take infinitesimal element of length in the phi cap direction, we can write it as r sin theta d phi. In short, if we take infinitesimal displacement, then the general term becomes dl vector equal to dr r cap plus r d theta theta cap plus r sin theta d phi phi cap. Here the value of r goes from 0 to infinity, the value of theta goes from 0 to pi, the value of phi goes from 0 to 2 pi. Now, if we take infinitesimal volume element dv, we can write it as dl r, dl theta, dl phi, and we already know the value of these three, so we can just put the value and we get r square sine phi dr d theta d phi. Now, if we take gradient, of in this spherical polar coordinate, we get del of f equal to del f del r cap plus 1 by r del f del theta theta cap plus 1 by r sin theta del f del phi phi cap. If we get divergence, in the spherical polar coordinate, the formula for it is 1 by r square del r of r square ar plus 1 by r sin theta del theta of sin theta a theta plus 1 by r sin theta del a phi del phi. The formula for curl in spherical polar coordinate is del cross A equal to 1 by r square sin theta r cap r theta cap r sin theta phi cap. Then we can write del r del theta del phi and a r a theta r sin theta a phi. Now, if we write the Laplacian in spherical polar coordinate, the value will be del square f equal to 1 by r square del r of r square del f del r by r square sin theta del theta of sin theta del f del theta plus 1 by r square sin theta del 2f del phi square. Now, if we talk about cylindrical polar coordinate, polar coordinate. In case of cylindrical polar coordinate, we have three coordinates r, phi, z, and if we take a Cartesian coordinate which is x, y, z and take a arbitrary point P, we connect the origin O and the point P, then draw a perpendicular from the point P on the xy plane, then join the point O and Q now join the component of z axis and P, we get we take this angle as phi, this straight line as r, then if we take the direction of unit vector along this point P, we get that r cap is along the direction of r, phi cap is along the direction of phi and z cap is the remaining direction. In this case, we can write this straight line has a length of r. So obviously, as this straight line and this OQ straight line is parallel to each other, so this OQ straight line will also have a magnitude of r. So we can write x as r cos phi, y as r sin phi and z as z. If we talk about infinitesimal displacement, that will be dl of r is dr, dl of phi is r d phi, dl of z is dz. So the general infinitesimal displacement will be dl vector equal to dr r cap plus r d phi phi cap plus dz z cap, and the volume element dv will be r dr d phi dz, where the value of r will be from 0 to infinity. The value of theta, sorry, there is no theta here, the value of phi will be 0 to 2 pi and the value of z will be from minus infinity to plus infinity. If we try to find gradient in cylindrical polar coordinates, it will be del of f equal to del f del r cap plus 1 by r del f del phi phi cap plus del f del z z cap. Next, divergence will be del dot a equal to 1 by r del r of r a r plus 1 by r del a r by del phi plus del az del z. Now if we take curl, that will be del cross A equal to 1 by r cap, r phi cap, z cap, del r, del phi, del z, ar, ra phi, az. Next is Laplacian. Laplacian will be del square f equal to 1 by r del r of r del f del r plus 1 by r square del square f del r square. Sorry, this is not del r square, this will be del phi square plus del square f del z square. So this is how we write both in cylindrical polar coordinate and in spherical polar coordinate. Now the next topic that is needed to be discussed is Dirac delta function. Dirac delta function. In case of Dirac delta function, we take a single point and we assume that this particular function, okay, let us consider the function as 1 by r square r cap, and this function is radially outward always. Now if we take divergence of this function, we will get that as this we are taking a point, so this can be considered as a sphere, and that is why we will take the divergence formula in spherical polar coordinate, and that will be 1 by r square del r of r square and the value of function, that is 1 by r square. So by doing this we get 1 by r square del r of 1, and that gives us the value 0. So divergence of this particular function is 0. However, if we take surface integration of this function, we get 1 by r square into r cap, that is the function a vector, and for the value of ds we get r square sine theta d theta d phi r cap. So if we integrate it further, then we get from 0 to phi sine theta d theta and 0 to 2 pi d phi. Here we have divided r square by r square and multiplied it, and we know in case of dot product this values will be multiplied, and then we get this value, that sine theta d theta d phi, and then we integrate this for the value of theta 0 to pi, and for the value of phi, that is 0 to 2 pi. All thing is considered in spherical polar coordinate. So we get the value 4 phi by integrating this. Now we can see that by doing divergence, we get the value of divergence as 0. However, the value of the surface integral is 4 phi. So because we already got that the value of divergence is 0, so if we take the volume integration of this function, that will also be 0, as the del dot A or the divergence is already 0. So this, but we know that from the divergence theorem, this value is equal to this value. So from the divergence theorem we are getting that these two should be equal, but as we can see that these two are not equal. So why is this? Now this is the case only for origin. So if we take a look at the picture here, that we are taking this as at a single point. So at a single point this will be different. And we can see that this surface integration is 4 pi, which is independent of the value r. So if we take that divergence theorem is right, then the value should be 4 pi for the volume integration also, but we are not getting that. This is the property where that this particular function becomes 4 pi everywhere except the origin. So this is we already know that no ordinary function can behave like that. So this type of function is known as this type of function, in this example the function like a vector, is known as Dirac delta function. Now let's talk about the one-dimensional Dirac delta function. That is, del of x becomes 0 if x not equal to 0, and del of x becomes infinity if x equal to 0. If we draw this in a graph, the value of x should be, when the value of x is 0, the value of del x is infinite. So we can draw it like this, that the value of x is, the value of del x is 0 everywhere except at the point x equal to 0. So this is known as Dirac delta function. And if we take infinity, if we take integration from minus infinity to plus infinity of this Dirac delta function, we get the value 1. We can also write that for Dirac delta function, fx del x equal to f0 del x, and del of x minus a equal to 0 to infinity. Del of x minus a will be 0 if x not equal to a, and del of x minus a will be infinity if x equal to a. Now this comes from the previous formula, that is del of x. Now if we put the value x minus a in the place of x here, we can see that x minus a will be 0 when x minus a not equal to 0. That means we can write it as x not equal to a. So from this formula is made. Again, f of x into del of x a becomes f of a del of x minus a, and minus infinity to infinity f of x del of x minus a dx. This gives us the value of f of a. This is the properties of Dirac delta function. Again, three-dimensional Dirac delta function that will be del cube of r vector equal to del of x, del of y, del of z. Again, if we take integration over all space for this Dirac delta function, which will be volume integration, the value will be 1. And if we take integration of all space f of r vector del cube of r vector minus a vector r vector dv, that will be f of a vector. We also get del of r cap by r square which gives us the value 4 pi del cube of r vector. So these are the properties of Dirac delta function. The next topic is the theory of vector fields. The first theory is for irrotational field. For irrotational field, irrotational field means that del cross A equal to 0. So for irrotational fields, there will be del cross A equal to 0 always. Number 2 is integration A to B A dot dl is independent of path. Number 3 is closed integration f dot dl is the closed integration A dot dl is 0 for any closed loop. And the fourth one is A vector. We can write this as a gradient of some scalar, that is A vector equal to minus grad V. Now for the next theorem, is for solenoidal fields. Solenoidal fields is del dot A equal to 0. This already happens, we know, for solenoidal fields. Number 2 is A dot ds is independent of surface. Number 3 is A dot ds is 0 for any closed surface. And number 4 is A is a curl of some vector, that is, we can write it as A vector equal to del cross V vector. So we can write A as a curl of some vector.